Good morning all. In this video, I will discuss about the boundary conditions for transverse magnetic and transverse electric waves. Why I am doing such a video is because after watching my videos on waveguides, recently somebody asked me why the boundary conditions for TE and TM waves are different. For example, in the case of transverse electric waves, the boundary condition is dou Bz by dou n equal to 0 on the surface. But in the case of transverse magnetic wave, the boundary condition is Z component of electric field is equal to 0 on the surface if you are considering a wave propagating in the Z direction. So why the boundary condition for electric field and magnetic field are different in the case of TE and TM waves? That was the question. So in order to answer that question, I am doing this video. Now, the important thing is when you consider the propagation of waves in presence of a metallic conductor, what is the difference? For an electromagnetic wave propagating in the Z direction, if it is in the free space, we have the electric and magnetic fields as E equal to E0 e raised to I kz minus omega t, B is equal to B0 e raised to I kz minus omega t. Here we are assuming that it is a traveling wave in the Z direction and the time dependence is also sinusoidal. And the media is homogeneous media. In the sense, all directions are same for the wave. And in that case, the amplitude E0 and B0 are constants. They are independent of x, y, z. So this E, even though I represented it as a function of x, y, z, t, it has only dependence on z and t, and both the dependence I assumed that it is sinusoidal. I am assuming or I am considering a sinusoidal wave propagating in the z direction. If the same wave, if you consider in presence of a metallic conductor, for example, if you guide this wave between two parallel planes, or if you guide this wave in a waveguide, then there are presence of metallic conductors. In that case, the amplitude E0 and B0 are not constants. They will depend on the space coordinates. Again, assuming that the wave is propagating in the z direction and the dependence assumed is sinusoidal, so you can take the z dependence as e raised to I kz. Also, the wave is sinusoidal in time also. So the z dependence and time dependence is same in the earlier case, but the amplitude part will depend on xy coordinates. So that is the important difference when you considering the propagation of wave in a non-homogeneous media. Now, this electric field and magnetic field here are vectors. So I can consider the three components. E0, the x component is Ex, y component is Ey, z component is Ez. All these components will be function of x and y. For a wave propagating in a homogeneous media, all these components are constants, but here these components are functions of x and y. Similarly, B0 you can write it as Bx, xy plus By of function xy, Bz function of xy. Now, the wave equation for electric field is del square E is equal to 1 by c square dou square E by dou t square. Now, assuming the dependence on z as e raised to I kz, taking two derivatives with respect to z, you will get it minus k square, and taking two derivatives with respect to t, you will get minus omega square. So substituting that in this equation, because del square in Cartesian coordinates it is dou square by dou x square plus dou square by dou y square plus dou square by dou z square, Whenever you have a dou square by dou z square, you can replace it with minus k square by assuming a sinusoidal dependence along z. Then whenever you have a dou square by dou t square, you can replace it with minus omega square. So this wave equation reduces to this one, and you can write it like this, okay, because this exponential part you can neglect, and this part should vanish. Dou square by dou x square plus dou square by dou y square plus omega square by c square minus k square into E0 equal to 0. Similarly, dou square by dou x square plus dou square by dou y square plus omega square by c square minus k square into B0 equal to 0. These are vector expressions. So this is equivalent to 3 equations, one for Ex, one for Ey, and one for Ez. This is also equivalent to 3 equations, one for Bx, one for By, and one for Bz. Among the 6 equations, we are going to consider only 2. Okay, we are going to consider only the z component of the equations. So that becomes dou square by dou x square plus dou square by dou y square plus omega square by c square minus k square into Ez or Bz equal to 0. So this is actually 2 equations. By solving these 2 equations, we can find Ez and Bz provided there are suitable boundary conditions on Ez and Bz. So if we have a boundary condition for Ez and Bz, we can solve this equation in order to find Ez and Bz. Now, our aim is to find all the components. Okay, so we need to find Ex, Ey, Bx, By. How can we find that for components? We have the Maxwell's equation del cross E equal to minus dou B by dou T. In component form, that becomes these 3 equations. This is you can write del cross E, and you can take the x component, y component, j component, k component or z component, x, y, z component. So you will get 3 equations. Similarly, del cross B equal to 1 by c square dou E by dou T. That becomes these 3 equations. Okay. So here also I assumed that dou by dou is ik. Whenever you have dou by dou T, you can replace it with minus I omega by taking sinusoidal dependence on z and t. Okay, so solving these 6 equations, we can find the value of Ex, Ey, Bx, By. I am not doing the entire calculation. This is a very simple mathematics. Rearranging these 6 equations, you can find Ex, Ey, Bx, By in terms of Ez and Bz. That is, the right hand side you have only Ez and Bz. Okay, the concept is that once you have Ez and Bz, you should be able to calculate this other 4 components Ex, Ey, Bx, By. Okay, so the procedure is, first you solve this equation in order to find Ez and Bz with the suitable boundary conditions. Once you have the value of Ez and Bz, use these 4 equations in order to find Ex, Ey, Bx, By. That completes the solution. Okay, now what is the importance of boundary condition? In the case of electrodynamics, the boundary conditions are always the tangential component of E is continuous across a boundary. Normal component of B is continuous across a boundary. These are two standard boundary conditions. Okay, tangential component of E is continuous, normal component of B is continuous. Suppose this is an interface. Say one side is air, the other side you have metal, and this is the normal direction between across the interface n cap. Then what is the meaning of tangential component of E? That is nothing but E cross n, E cross n, because when you consider E cross n, that will be perpendicular to the direction of n cap, otherwise it will be tangential to the interface. Okay, a cross product is actually perpendicular to both the vectors. So when you consider this cross product, that will be perpendicular to n cap, and that is in the plane of interface, that is tangential to the interface. So tangential component of E is continuous means E minus EC cross n cap equal to 0. Here E is the electric field in air and EC is the electric field in the metal or conductor, that is why it is EC. What is normal component? Normal component means a component in the direction of n cap. So you have to take dot product. So B minus BC dot n cap equal to 0. That is normal component of B. It is continuous means B dot n cap is equal to BC dot n cap. So I can write it as B minus BC dot n cap equal to 0, where B is the magnetic field in air, BC is the magnetic field in metal. So the usual boundary condition, tangential component of E is continuous, becomes E minus EC cross n cap equal to 0. Normal component of B is continuous, becomes B minus BC dot n cap equal to 0. But if we assume that the metals are perfect conductors, we can take EC and BC as 0. So the first equation becomes E cross n cap equal to 0 and the second equation becomes B dot n cap equal to 0. These are the boundary conditions across a perfect conductor. Now consider the special case of a rectangular waveguide. These are true for any electric field and magnetic field in presence of perfect conductors. Now I'll consider the propagation of electromagnetic wave inside a rectangular waveguide. That is, the four walls are perfect conductors. I have a wall at x equal to 0, I have a wall at x equal to a, then at y equal to 0, y equal to b. Okay, and I am assuming a wave which is propagating in the z direction. The boundaries are at x equal to 0 and a, y equal to 0 and b. Now, the first boundary condition, E cross n cap equal to 0 becomes Ey equal to 0 and Ez equal to 0 for x equal to 0 and a. What is the meaning of x equal to 0? X equal to 0 is actually this yz plane. In this yz plane, what is the tangential components of electric field? It is simply Ey and Ez. And in the xz plane, for y equal to 0 and y equal to b, that is parallel to xz plane, the tangential components are Ex and Ez. Okay, so E cross n cap equal to 0 takes the form Ey equal to 0 and Ez equal to 0 for these two walls, x equal to 0 and x equal to a. And for y equal to 0 and y equal to b, that will take the form Ex equal to 0, Ez equal to 0. Here I represented the n cap direction, the direction perpendicular to the interface. Okay, so for x equal to 0, the n cap direction is in the x cap direction, So the tangential components are respectively Ey and Ez. I think it is clear why I am writing like this. Okay, now we are interested only in the boundary condition for Ez. We are not bothered about Ey or Ex. We are interested only in the boundary condition for Ez because we want to solve the wave equation for Ez only. Okay, so we are not bothered about the boundary conditions of Ey or Ex. We have Ez equal to 0 on all boundaries. X equal to 0, x equal to a, y equal to 0, y equal to b. At all boundaries, Ez is 0. So I can generalize the statement as Ez equal to 0 at all surfaces. At all the boundary surfaces, Ez equal to 0. I think it is clear. Now, the second boundary condition, B dot n cap equal to 0 becomes, for x equal to 0, this plane, yz plane, what is the n cap direction? It is the x cap direction or I cap direction. Okay, so I can write Bx is 0. Magnetic field component in the x cap or I cap, that is the x component of magnetic field. Bx equal to 0 for x equal to 0 and x equal to a. Similarly, By equal to 0 for y equal to 0 and y equal to b. Clear? The normal component for x equal to 0 and x equal to a interface is actually the x component of magnetic field. And the normal component in the case of y equal to 0 and y equal to b plane, that is the xz plane, that normal component is magnetic field y component, By. That is why this boundary condition takes this form. But the problem is, here we got the boundary conditions for Bx and By. But we need the boundary conditions for Bz, because we have the wave equation for Bz. In order to solve that wave equation, we need boundary condition for Bz, not for Bx or By. So, how can we attain a boundary condition for Bz from this? It is very easy. We consider the equations for Bx and By here. We have equations for Bx and By. Substitute the boundary conditions for Bx and By here. Then try to obtain a boundary condition for Bz. That is the idea. So what is Bx? This one. Okay. Bx equal to 0 means this quantity is 0. But already we know Ez is 0 at the surface. All these we are doing at the surface. So Bx is 0 at the surface, Ez is 0 at the surface. That means dou Bz by dou x is 0 at the surface. And that is true for Bx 0 for only for x equal to 0 and x equal to a. So for x equal to 0 and x equal to a, dou Bz by dou x 0. By, we have this equation. For y equal to 0 and y equal to b, By is 0. Also Z is 0. That means dou Bz by dou y is 0 for y equal to 0 and b. Now, for x equal to 0 and a, dou Bz by dou x is 0. This is x equal to 0. This is x, yz plane. X equal to 0 and x equal to a. Dou Bz by dou x, that is the derivative of Bz along the x direction. That is along the normal direction. For y equal to 0 and y equal to b plane, dou Bz by dou y. Dou Bz by dou y is again the derivative of Bz in the direction of y, that is in the normal direction. So we can generalize this as dou b by dou n on the surface is 0. Dou b by dou n on the surface. Dou n means for the case of x equal to 0 and x equal to a, that n becomes x direction. And for y equal to 0 and y equal to b, this n becomes y. So these two equations together we can write dou b by dou n at the surface is 0, where n represents the normal derivative. Dou b by dou n means not dou b, it is dou bz. Sorry, dou bz. Dou bz by dou n at the surface is 0. So in the case of electric field, the boundary condition is simply Ez equal to 0 at all surfaces. But for magnetic field, not Bz equal to 0 at surfaces, but dou Bz by dou n is 0 at the surface. Okay, so this boundary condition is obtained from this standard boundary condition. And why this is different? Because here we obtained boundary conditions for Bx and By, but we need a boundary condition for Bz. So from these expressions, we will get a boundary condition for the normal derivative. And when you solve the TE wave, transverse electric means electric field have only transverse components, that is Ez is 0. There is no component in the propagation direction. Ez equal to 0 at all points inside waveguide. So there is no relevance for Ez equal to 0 on the surface. That's boundary condition, because Ez is 0 everywhere. Okay, so we are not going to solve this expression, this wave equation Ez is 0. So we have only one wave equation for Bz. So you just solve the wave equation for Bz with the boundary conditions of Bz, and that boundary condition is simply dou Bz by dou x at x equal to 0 and a is 0, dou Bz by dou y at y equal to 0 and b is 0. Okay, when you try to solve a TM wave, then Bz is 0 everywhere. TM, transverse magnetic. So magnetic field is transverse only. So then you have Bz equal to 0 everywhere. Then there is no wave equation for Bz. You have only wave equation for Ez. So solve that for Ez. the boundary condition for Z will be Z at surface is 0. I hope now it is clear. So thank you for watching.